Hi, I am Erik at the University of Tokyo in the group of Kaoru Yamanouchi. And I also want to mention our excellent master student, Ryuhei Yoshida. And we are collaborating with Yutaka Tachikawa's group at the DIC Corporation. And I'm very happy to be here at this very interesting conference. I learned a lot about different approaches to quantum computing, which I did not know about before. So we have a collaboration with the DIC Corporation. It is done within the QIIC, so Quantum Initiative of the University of Tokyo. We call it Aquabit, Applied Quantum Chemistry by Qubits, and we made a kind of colorful picture. But basically, we are interested in applying quantum computers to physical chemistry problem or quantum chemistry problem. So some recent project which we have done are the calculation of vibrational energy of molecules, so for vibrational spectroscopy. And this paper here in press was actually published today, this morning, Japanese time. So please check this AVS Quantum Science latest or the latest paper there if you are interested. And then time-dependent simulations we are trying to do, but and also some kind of electronic structure, so Hückel molecular orbitals. And today I will tell you about these two, this top one, vibrational energies, and the Hückel orbital calculations. But before I go into the details of those two projects, I want to make a kind of statement or something that we realized, something which we think is useful to how to think about the quantum computers. So especially then the quantum computers which we have access to today. And as you know, there is a lot of noise on the present-day quantum computer. So the decoherence and the gates are not perfect. So in the end result, there is error. So to get a meaningful result out of the calculation, we must correct for this or mitigate the error after the calculation. And then we find it useful to think of the calculation on a quantum computer as an experimental measurement. So we have to deal with both systematic and statistical errors when we do the calculation of the quantum computer. This, of course, is something, as the experimental scientist, we are used to this. Every time we do an experiment, we must deal with both systematic and statistical errors. But as a theoretical scientist, this is maybe not what we are used to. We are used to just to run our program and get the same result out every time. But on the quantum computer, it is not as easy. Okay, so then to the first project or the first topic is the quantum mechanical vibration of molecules. So molecules vibrate in many different ways, and because molecules are quantum mechanical objects, this vibration, the energy of the vibration is quantized. So you get the kind of discrete energy levels. So the example here, I show the CO2 molecule. So it can vibrate. There are three modes, so stretching and bending and asymmetric stretch. And the energies then are quantized like this. So the energy levels are quantized. And for CO2, the excited state here called the Fermi resonance or the Fermi doublet is an interesting, well-known feature of the CO2 vibrations. And for CO2, it is a small molecule, so we can calculate these levels. But if we have a large molecule with many vibrational modes, to obtain these discrete energy levels, it becomes a very hard problem if you want to solve it on a classical computer. So we thought that we would try to see if we could obtain this kind of energy levels on the quantum computer. So to do that, we simplify a little bit. So we stay with CO2, but we adopt this kind of two-mode model of CO2. So we only include these two modes, stretching and bending. So this, if you recall, these are the two modes involved in this Fermi resonance. And the model is a standard one. So there is one term in the Hamiltonian describing the individual oscillations of the mode. So this is harmonic as an harmonic oscillator. And then there are the terms coupling the modes. And we expand this in terms of the harmonic oscillator basis functions. And 16 basis function, very small kind of test problem we are considering. And so 16 basis functions means that we can describe this using 4 qubits on the quantum computer. And then we came up with then a method which we called restricted multi-state contracted VQE. So it is a kind of variant or an extension of a method previously proposed by Martinez group. And the main idea is to introduce basis sets describing the vibrational wave functions, and 2 kinds of basis set. One basis set, phi n, and then psi n depending on variational parameter theta. So it is a kind of variational VQE method. Then we calculate matrix elements of these basis sets. And the matrix elements involving this basis set, is calculated using the quantum computer. The basis sets involving the other basis set, phi n, is calculated on the classical computer. So by construction, it should be so that this one is, even for a large molecule, this can be done efficiently. And these matrix elements are supposed to be difficult to calculate on the classical computer. And then after constructing the Hamiltonian, we diagonalize using the classical computer, using the standard eigenvalue algorithm. And then because there is a variational parameter, or in general, then many parameters, we can change this parameter so that the energy levels becomes as good, so as we would try to lower the energies of all the levels, or the sum of the energy levels, as much as possible. Then, what about the error mitigation? So we, to actually get something which agrees more or less with the reference result, we have to correct these matrix elements, which we calculate on the quantum computer. And the view graph I show here is the one of the matrix elements evaluated on IBM's quantum computer, so the IBM Kawasaki machine, which was installed last year in Shin Kawasaki. And then this is the exact reference result. This is the right answer. It should be like this. But when we evaluate the matrix element on the IBM Kawasaki using 4 qubits, we get this kind of distribution, which, there is a width here, so there is some statistical uncertainty, but it is also shifted with respect to the exact one. So we must find some kind of way to correct for this shift. And then what we came up with was the idea to evaluate the matrix element again, but at this variational parameter theta equal to 0. And then by construction, it is so that the theta equal to 0, it can be evaluated. This one, of course, this is the one measured on the quantum computer, but also this exact value can be obtained on the classical computer efficiently, even for a large system. This is still CO2, so this is no problem of calculating on our desktop, but of course. But even for a large computer, this large molecule, we could obtain this one. And then we estimate this shift here in the theta 0 case and assume this shift is the same as for the theta non-zero, so the optimal parameter. And this is not a general method, but at least in this case, it seems to work. So then we shift, this one is then shifted by the same amount as this one here, and then it comes much closer to the exact value here. So the measured distribution overlaps the exact value. So we calculate all the matrix element, and we error mitigate, and then we get this kind of distributions for the 2 Fermi resonance levels. So upper plots here are the before the error mitigation 2 energy levels. So this one is the right answer. It should be here, but it is shifted to here. So this should be here, but it is shifted. But after the error mitigation, or error mitigating all the matrix elements and diagonalizing, then we get the distribution which overlaps or it comes very close to the exact answer. It is not exact, but the uncertainty, the error here is 0.1 centimeter minus 1, which we are quite happy with. And then, the details, please check this paper, which should be, it was published today, in fact, in this ABS Quantum Science. Okay, then this is about the vibrational calculation of vibrational energy levels of molecules, which can be useful then for the vibrational spectroscopy. Next project which we did is related to the Hückel model. So Hückel model is, if you are a chemist, or then you know about this Hückel model. It is maybe the old and maybe most fundamental model in the physical chemistry. So it is a model of interaction of the pi electrons in organic molecules. So there are so small organic molecules with carbon atoms. And then the pi electrons in those molecules can be approximately described by Hückel model. And it is a kind of tight binding model. So only electrons which are on neighboring carbon atoms interact. And then I should say that this model is not something that is difficult to solve classically. So we cannot demonstrate quantum advantage or so, even if we have a very large molecule. But we thought that it could be, because it is a very fundamental model, it could be a good test for the quantum computer, simple enough to run on the computers which we can use today. And also it can maybe be a kind of first step to do something more involved with the involving the more like the electron-electron interaction. Anyway, so the idea is something like this: that we have the pi electrons. Pi electrons are the electrons which are described. The wave function are described by 2p orbitals on carbon atoms. So this shows the 2p orbitals in the benzene molecule. So there is one electron, so one atomic orbital on each carbon atom. And if we add them together, so a superposition of these atomic orbitals becomes then a molecular orbital like this. And the Hückel Hamiltonian then tells you what are the energies of these orbitals. So the energy levels which we can calculate and which is familiar then from the chemistry textbooks is like this, that there is the lowest orbital here, so no nodes, and next one with one node, and these would be the occupied orbitals in the ground state. And then the next one, then the unoccupied ones have more nodes, and the last one, then the highest one has there are three nodal lines. So we would like to try to calculate these, to reproduce these energies here using a quantum computer. And then we represent the orbitals, then we represent in a kind of direct way by saying that an orbital on the ith carbon atom is represented by a qubit state where the ith qubit is in the excited state. So all the qubits are 0, 0, 0, 0, and only one qubit is in the excited state 1. So for example, for these two carbon atoms, this ethylene molecule, then we have then two p orbitals, and one is described by the one, we say this is the 0, 1 qubit state, and the other one is the 1, 0 qubit state. And these kind of states can be easily represented just by inserting the x gates like this. And then to make the molecular orbitals, we introduce a excitation operator, we call it. So there is a mapping then from the basis function, and then by operating this operator on the atomic basis function, we make the superposition. And, this is the molecular orbital. So from atomic orbital, applying this excitation operator, it becomes molecular orbital, so a superposition. And this operator here, you can think of it as a unitary matrix. And this one then we will represent as a circuit on the quantum computer. And to get the right orbital, we have to then tune this parameter theta so that we get out the right molecular orbitals. And This can be shown then by using some mathematical considerations from previous research that we can represent any molecule, any Hückel orbital of any molecule. We can represent like a kind of product of smaller parts orbitals, so one here, and there are many of these. But if you put together these so many parts, and then you adjust the parameters, we can represent any unitary operator we can represent like this. And I want to stress here that we are using this operator, the quantum circuit, is the same for all molecular orbitals. So the only thing which changes, which is going to make like ground state molecular orbital or higher excited molecular orbital, is the initial one. So each atomic orbital is mapped to a different final molecular orbital. And then, each one of these parts here, you can show that most efficient way to write it is like this. This is one part here with having two C0 gates. And then, first, one word about the Hamiltonian. Hamiltonian then can be written as a kind of sum over all the bonded carbon atoms. So you have one term here per bond, per CC bond. But then it is better to rewrite this a little bit so that we can measure the energy at the same time as we measure the state. So this, as I will show you later, this we are going to use for the error mitigation. So at the end, to get the energy of the molecular orbital, we create the molecular orbital by this part here, so atomic basis function, and operating this one, and then attaching this additional term here to measure the energy. And this, so in this case here, we measure then we can calculate this expectation value at the same time as measuring the probabilities of the population of the qubit states. So a typical circuit for the cyclobutadiene is like this. So first part, we create the starting atomic orbital. So we have an X gate here. So this should be the ground state orbital. And then different pieces, different 2-qubit operators are patched together to create the unitary matrix representing to make the mapping from atomic orbital to molecular orbital. And at the end, we attach one gate here, which represent in this case that we measure the bond between carbon atom 0 and 1. So, okay, there are no numbers here, but let's say this one here, or maybe this one. It doesn't matter. But you have to measure then each bond energy separately. So there is a certain kind of symmetry, beautiful symmetry in this construction here. Yeah, then about the error mitigation. In this here, we applied also a kind of simple version of the error mitigation, simply just throwing away the unwanted states. So because we can measure the energy of the orbital at the same time as the population of the states, so we can get some kind of diagram like this, that for this C2H4, we should only measure this one 1, 0, and 0, 1. We should not get the 0, 0, and 1, 1. But we still get some small probabilities here for 1, 1, and 0, 0. So in this case, then the error mitigation is just that we throw away this one, and throw away this one, and normalize again. And then it becomes a little bit better. And the resultant for ethylene here and benzene here is shown in this slide here. So you should go from maybe look from the bottom up. Yeah. So this is without error mitigation as it comes out from the measurement on the quantum computer. Then with error mitigation and exact result. So this upper row here is the right answer. And for this small one, 2 qubits, then it is quite good. But for 6 qubit, the benzene, the error mitigated one is maybe 10% or so. So it's it should be this yellow one, but it is shifted by 10%. And also the degenerate states are actually split because of the noise. As a next step, then maybe we could try to apply, combine this with other more sophisticated error mitigation methods. So as a summary, I showed you what we are doing in our Aquabit project. We are evaluated the vibrational energy levels of CO2, this Fermi doublet. We could evaluate quite precisely. We are quite happy with this. And also showed the quantum computation of molecular orbitals in the kind of very simplest model possible of molecular orbitals. And next step should be to go to more sophisticated models. Thank you very much.